Okay, so morning, everyone. In this talk, I want to present some calculations which we performed in the last couple of years, and I want to focus a little bit on the technical developments which allowed us to do so. And since this is the first talk of this type during this kickoff conference, I want to introduce the various techniques, basically from scratch. But I will also talk a little bit about the more recent developments, and please feel free to interrupt me anytime. So the topic of my talk are scattering amplitudes for LHC physics, and as we learned, the level of precision we're aiming at for predictions for the Large Hadron Collider require higher order perturbative calculations, and one of the main bottlenecks in these computations is the calculation of these multi-loop integrals. And it is maybe not a big issue to write down some expression for these multi-loop amplitudes. So at the level of the loop integrand, you have different options to write that down. And I've listed a couple of options here. Roughly speaking, you write your matrix element or scattering amplitude as a linear combination of some building blocks, some loop integrals, with some coefficients, and you have different options for that. For instance, you could directly use tensor integrals, and then you have tensorial coefficients. What we mostly do nowadays for multi-loop integrals is we express everything in terms of scalar integrals, and then these coefficients here at this level are rational scalar functions of the kinematic invariance and the space-time dimension D. Notice that I have factored out the spinor factor such that what remains is actually a Lorentz scalar, and everything connected to the little group weights is absorbed in here. But so what I have in mind is to compute helicity amplitudes in that way. Now, you can also go one step further and decompose with respect to a set of master integrals, so a smaller number of linearly independent loop integrals, and you have different options to do so. Or if you are able to solve these analytically, you may directly decompose your amplitude with respect to some functional basis. So once you are at the level of loop integrals, you can put everything on the computer by writing down a complete set of propagators and then index your integrals in this way. So in this way, you can express any scalar loop integral. And the crucial point here is that if you consider different exponents for these propagator powers, so possibly even inverse powers, such that you put something in the numerator, you will find that out of all these infinitely many integrals, not all are linearly independent. In fact, almost all are linearly dependent. You have only a finite basis of basis integrals or master integrals. So you can think of these linear combinations of loop integrals as forming a linear vector space with some basis. And one of the main challenges is to reduce with respect to some chosen basis, and then, of course, to evaluate the remaining basis integrals. In this talk, I will also mention some progress regarding these rational coefficients, which is actually also a computational challenge, because these can get big if you have multiple scales. And I will comment on some recent developments which allowed us to deal in a better way with these. And then I will also show some results. So let me start with the integral reductions. In dimensional regularization, the integral over a total derivative vanishes. Now, if you evaluate this at the level of the integrand, you get a relation, a linear relation between different loop integrals. And in principle, you can choose different powers here and write down many of these relations, combine them, and solve this linear system of equations, and in this way achieve a systematic reduction of an arbitrary integral down to a basis of loop integrals. So in principle, you can give this to anyone without additional knowledge, and in principle, it's totally clear how to do this. The challenge in practice is that these systems get big. So maybe you have 10 to the 9 integrals or something, and then formally you have to solve a 10 by 9 by 10 by 9, 10 to the 9 by 10 to the 9 matrix, and as you can imagine, this can become a challenge. Of course, this matrix is totally sparse, so otherwise you couldn't do anything, but still, the exact way how you do it deserves discussion. And different approaches have been discussed in the literature. Let me mention some of the more prominent ones. To start with, there exist various public codes, but sometimes they even though a lot of experience went into the creation of these codes, sometimes they can face challenges for state-of-the-art calculations. And different strategies have been imposed to make progress with more challenging systems. Roughly speaking, you can divide the different approaches into things dealing with symbolic exponents, and then a step which I call the Laporta step or Laporta algorithm, where you plug in integer numbers for the exponents, and you deal with explicit integrals rather than symbolic general solutions. And yeah, some of the more powerful approaches combine some preparation at the symbolic level with some step afterwards where you plug in the explicit integers. And a rather new approach, which falls a little bit outside of this domain, is provided by intersection theory, but as of now, this is not really being used for the most complicated calculations. So one of the ways to deal with these big systems, and in particular with the intermediate expressions, well, at the level of these rational functions. So we're dealing with big matrices, and the matrix entries are rational functions of different variables. And if you perform these row reductions, for instance, then these can grow big, so really big. And in order to avoid the whole thing blowing up, only to collapse at the end for the calculation of the physical quantity of interest, you can circumvent this to some degree by doing the following. You can plug in numbers for all of your variables, and then you get a rational number instead of a rational function. And this rational number can be mapped modulo, for instance, some prime field, and then you end up with something which is a machine-sized word, something the computer likes. Then you perform all your manipulations over this prime field, and this way nothing ever gets big at the level of an individual coefficient. And then you do this many times to probe the structure, and at the end you reconstruct the symbolic information of interest. Now, the crucial point is that at intermediate stages, nothing gets big. And also, you can choose to reconstruct a simple quantity rather than some intermediate step where things are still big. And most of the really challenging calculations nowadays use these finite field and rational reconstruction techniques to some degree. So this is an illustration of what happens if you just write down some matrix element in terms of unreduced integrals, and you do traditional symbolic algebra for the IBP reduction. Then yeah, you have this blow up, and then you get something usually smaller at the level of decomposition with respect to mass integrals. then maybe you want to perform some partial fractioning to bring this down further. And if you have access to analytical solutions, at the end, you want to express it in terms of functional basis. And this is usually the level, if you do it right, where things become really small, like orders of magnitude smaller than what you had before. So this is to give you some idea about what I'm talking about here. So this is for a 3-loop calculation of 4-point functions, which we performed in collaboration with Pietro Baghiela, Fabrizio Carola, and Lorenzo Tancredi. So this is a PhD student. And you see here that at 1-loop level, 2-loop level, and 3-loop level, of course, the numbers rise for the complexity of the expressions. But what I want to point out here is that you go down with the number of integrals, of course, if you go down, if you choose mass integrals, and the size of your expressions prior to IBP reduction would be this. Then if you write it in terms of mass integrals, it becomes much smaller. And the final expression in terms of harmonic polylogarithms is, you see, several orders of magnitude smaller. So you may choose to circumvent this to some degree and directly reconstruct at a level which you like. However, in this case, we have a lot of permutation symmetries with respect to the external legs. So in that case, we actually chose to perform the reduction and reconstruct at an earlier stage, as you can see here, and then do the crossings at the symbolic level. Now, one thing which can help you to avoid complexity during the system solving is to avoid the introduction of squared propagators in the integration by part relations. If you apply a derivative operator to some 1 over something expression, in general, you square the 1 over something, right? This introduces many auxiliary integrals you're not really interested in, and you can avoid that to some degree using what is known as syzygy techniques. So here I've written down the setup in Bykhoff's parametric representation, but similar comments apply to the momentum space representation as well. You can express the absence of these squared propagators as so-called syzygy relations, where which you can think of as being some linear combination of known polynomials where the coefficients are polynomials in themselves. So you want to find these coefficients such that essentially a vector of polynomials times a vector of polynomials gives 0. This is what a syzygy is. And it turns out that you can use existing computer algebra codes for that, but at the end of the day, it can also be fast for the problem at hand to just use linear algebra as well, again, to produce these syzygies. And then you can exploit the toolbox of finite field techniques again, and so on. I want to advertise something else, which is not so frequently discussed. That is, you can also produce integration by part identities without the introduction of numerators. So if you just start with a scalar integral, maybe you don't see the point in introducing irreducible numerators in addition to what you already have. And then you could work with such a scheme where you never introduce new numerators. And also there, the construction proceeds via the computation of syzygies. Please feel free to ask if you are interested in learning more about this. I'm just flashing this here. So we studied the general structure a little bit further and found that how you can make this work in practice up to the for-loop level. So once you have your amplitude expressed in terms of some basis integrals, you still need to solve the integrals. So what do? Well, maybe if you feel lucky, you go to Loopedia and look up if someone else did the job for you. But if it's a complicated problem, chances are you won't find it, but you have to sit down and find a solution yourself. And different options exist. Working with different representations, you can choose to perform direct parametric integrations. And if you work with finite integrals, you can do this after expanding in epsilon, where epsilon is the dimensional parameter, the deviation from 4 dimensions. But in particular, in the presence of several scales, one of the most powerful methods is the method of differential equations, where you derive a differential equation with respect to some external kinematic invariant, and then solve this auxiliary differential equation if you want. And so you can always write down a linear system of differential equations of this type, where this I vector is a vector of basis integrals. You take a derivative with respect to some, say, mass squared or some Mandelstam invariant, and then you get again a linear combination of master integrals with some coefficients. This is a matrix here, and this will always work because you can always perform IBP reductions. So this is something you can always do. And then it turns out that by studying the homogeneous solutions, where with homogeneous I mean if you set epsilon to 0, if you get control over the homogeneous solutions of these differential equations, then you can perform a basis change, a basis transformation, such that you end up with a simpler differential equation where the epsilon dependence factors out front. And if you have that, that's much easier to solve. Then you can, for instance, apply the so-called symbol calculus and construct analytic solutions using computer algebra. And yeah, this is pretty well under control. Nowadays, we also know how to construct algebraic letters in a suitable way. So this is something which is relevant if you have internal masses. And probably Tauschif will tell us a little bit more about this for state-of-the-art integral calculations. So another technique which we found useful to compute for-loop form factor integrals is direct parametric integration. And the starting point for this is an observation which tells you that if you have an arbitrary loop integral in quantum field, in some quantum field theory, which has UV divergences or infrared divergences or both, then you can always decompose that integral in terms of finite integrals and make all the poles in epsilon explicit in the prefactors. So this is a totally general statement. This is an example of what I mean. This has divergences, and you can decompose it in terms of finite integrals. But here now the finite integrals have squared propagators or triplet propagators and live in higher dimensions in general. But otherwise, it's really the same type of integral. So in particular, you don't introduce any new spurious poles or new singularities which weren't there in the first place. And you see here that all the poles are explicit in the prefactors. If you have that, you can expand at the integrand level. And you can also use it to improve your numerical evaluations, because yeah, your computer program has to do less to evaluate finite integrals. So I want to point out that the exact choice of integral can also have a major impact on how complicated the expressions are that you're going to compute. I've written down different epsilon expansions for different integrals. And these are the terms I would need to get complete weight 6 information to be used in some amplitude calculation, say. And as you will notice, this is much longer, and also it involves transcendental constants up to weight 8, something which will drop out at the end of the day in your physical observable. But at this intermediate stage, you just need to expand to this order, because otherwise you don't get full weight 6 information. So yeah, this is to motivate that a good basis choice can be crucial to perform your calculation. You can also write down finite integrals as linear combinations of integrals which live entirely in 4 dimensions, say. If you want to do that, in general, you need to include also subsector or subtopology integrals and possibly numerators. But you can do so in one, combined Feynman parametric representation, and define in this way generalized integrals, which you can also then directly numerically evaluate. So now you have your amplitude decomposed in terms of mass integrals. The mass integrals are solved analytically or possibly numerically. You still have to deal with the coefficients. The coefficients can be quite sizable, and for univariate problems, the standard method, which has been used since a long time, is to use partial fraction decomposition to bring this into a unique form, which also shows you where certain structures grow large. For instance, here you would see for x going to -1, for instance, how the expression behaves. Now, the naive approach would be to just iterate this in order to apply it to the multivariate case. If you would do this here in some way, you would end up, for instance, with this decomposition. Now, what you see here is that on the right-hand side, you have a pole at y = 0. But this is totally spurious. The left-hand side didn't have that. And this is a general pattern. But you can avoid to introduce these spurious poles by doing a proper multivariate partial fraction decomposition. And I cited some work which aims at that. And these decompositions can actually help you to bring down amplitude expressions by up to a factor of 100 in size, going from the common denominator decomposition to or representation to this multivariate fraction decomposition. And the approach we take here is we define new variables for the inverse denominators. And now we have relations of the type Q, which is the inverse denominator, times denominator is 1. So you should read this as the whole thing is 0. And these relations are the relations you can use to simplify or manipulate your rational functions, right? So using these relations, you express your rational function as a linear combination of polynomials. And then you compute what is known as the Krippner basis of the ideal generated by these relations. And then you can systematically reduce these polynomials in such a way that you end up with the unique result. Now, this Krippner basis depends on the monomial ordering which you choose. And by adjusting this appropriately, you can ensure that certain features will be achieved in your final decomposition. And we proposed here a new ordering, which is different from what has been proposed before and is known as Lehnater's decomposition. And it aims at reducing the overall powers in the final expression. And this can also help you to improve the numerical performance, because you can make sure that you never introduce higher powers in these denominators than you absolutely need to. And in this way, most of the most severe numerical cancellations which lead to numerical instabilities are actually triggered by inverse powers. So that is useful in practice. And you can just download a Mathematica package if you want for that. So before I come to my final topic, I want to entertain you with a quiz. So now you have to pay attention and give me an answer, please. So that is with respect to the reconstruction of functions, so of rational functions. If you want to reconstruct the rational function, obviously it will help you a lot if you know already all the denominators, right? Then you have to reconstruct only the numerators. You need fewer samples for that. Now, there are methods to guess the denominators or the types of denominators you have in the problem. Once you have them, you can either use univariate reconstructions to find the multivariate denominators, or you can use the scheme which I want to discuss here. That is, suppose you know for some reason that this is likely the type of denominator factors you have in your expression. Now you can sample these denominators by plugging in some numbers for your variables. In this case, I've chosen them such that this is the prime factor decomposition of the result. And now you do your finite field sampling and rational reconstruction, and you know that for some expression, you get a rational function which has this denominator. Now, from this, can you tell me what the multivariate denominator factors are? So this is the result of the numerical evaluation. And now you want something to express in terms of these multivariate guys. So if you find it's obvious, then please say so. Sorry, what's the first one? D2 squared. That's right. Yeah, D2 squared. D3 cubed, right? Because the 3 appears only here, right? And then we have the 7 only here. So this is whatever. Sorry, this 7. Yeah. So the 7 should tell us what the D1 power is. Okay. Now, in principle, you don't. I mean, here I've chosen it in such a way that you have a unique prime factor to each of these denominators, so it's fairly easy to read it off. You don't necessarily need that. Now, are you 100% sure that these are the multivariate denominators, or what could go wrong? So one obvious source of mistake is, of course, if this is not complete, right? If there's another denominator factor which we didn't guess beforehand. The other thing could be that we have a numerical prefactor which has nothing to do like with the actual denominators. An explicit 1/31, for instance, could appear here, right? So then we could be fooled. Now, the good news is it doesn't really matter. It's just a guess. You just try to reconstruct a modified function where you just assume that these are the denominators. You multiply with these denominators, and then you just reconstruct whatever is left. So if your guess is wrong, you have to do more samples to reconstruct the function, but it's still, in general, actually, it works remarkably well, but it's nothing, which will, stop you from proceeding, even if the guess is wrong. And yeah, and I think we will hear more about more advanced techniques to guess the final decomposition and possible terms using p-adic techniques in the talk by Herschel, which is directly after this talk. So these techniques allowed us to achieve new milestones for the computation of multi-loop amplitudes in full color QCD. So for the first time, we computed 5-point functions at 2 loops, 4-point functions at 3 loops, and 3-point functions at 4 loops in full color QCD with these techniques. And now, in some cases, for instance, here, 2-loop calculations have been available using leading color approximations. And now you may say, well, okay, isn't that good enough? And the answer, it likely depends on what you're going to calculate, but it's not always so obvious that leading color is everything you want if you want to go to really high precision. So here I'm showing an example from a calculation for dye photon plus jet production, where you see here for the finite remainder, or rather the interference of that with the tree, and integrated over everything except for PT of the final state gluon. You see here the leading color approximation in comparison to the full result. You see that at this level, at the level of the finite remainder, it's really, not a great approximation. You get in the ballpark by including at least some of the fermionic corrections in addition, but in general, to match the curve, you also need non-planar contributions. I mean, this is not at the level of cross sections, right? This is at the level of finite remainder, right? So it's not totally conclusive, and also it will be combined with many other things and so on. But it's just something to be aware of, that you know, at the level of the finite remainder, leading color is not necessarily you know, spot on. Yes. PL is planar, so this is a little bit more than just leading color. It includes certain fermionic corrections, and these fermionic corrections tend to be important. And yeah, so they are also like typically easier to compute than the full color QCD. Well, okay, yeah. I mean, depends at what you're after, right? I mean, this has the wrong sign, right? Okay. Okay, if you. So yeah, I mean, the strict leading color would not involve the fermionic corrections, right? So okay, so maybe part of the message is you need the fermionic corrections, and you don't necessarily need you know, all contributions from them to get in the right ballpark. But in general, you know, you will need everything if you want at least, you know, 50% precision on the finite remainder. Okay, but I mean, this is just one example. It's easy to show other examples where the picture is different. Okay, so some of the results which we were able to derive from the 3-loop calculations for the 4-point functions. We worked out these 3-loop amplitudes with Fabrizio, Carola, Amlan Chakraborty, a young postdoc, Giulio Giambutti, a PhD student, and Lorenzo Tancredi in these papers. And so we computed all partonic channels. And this allowed us to check a prediction by Enan Gardi and collaborators for the general structure of the infrared poles at the 3-loop level. And this is the first time this has been checked really in full QCD, and everything matches perfectly. So in particular, we see that we have these 4 parton correlations, right? And then we have also 3 parton color correlations, which give rise to these additional terms, which violate, if you want, the previously conjectured dipole assumption for the structure of these poles. So this fits all nicely. And another thing which fits nicely is we've learned in the talk by Enan that they came up with a new way to predict the high energy behavior of general loop amplitudes. And they achieved this by separating the Ricci cut from the pole contributions. So following their scheme, we took our Fogg-Luan calculation and extracted the 3-loop Regge trajectory, which was at the time the last building block for this single region exchanges at next to leading order. And we found this result. And in parallel, we have checked this with an independent extraction by Enan's group, and we found, of course, a perfect agreement. Otherwise, you would have heard about it before. And so we also extracted these ingredients and the impact factors from the other partonic channels. And so this gives overcomplete information. So this is not just a fit anymore. It's a validation now of the framework, because it's a non-trivial fact that if you extract these parameters from the different amplitudes, that you get the same result. And everything fits just nicely. So how much time do I have? -3? Okay, so I'll be very quick. I'll be very quick. In the last few minutes, I want to talk about some new calculation which we have been performing for for the for loop splitting functions. So I can be very brief with the introduction because Giulio gave this nice talk already. The crucial point here in the following is that you can extract the splitting functions from anomalous dimensions of twist2 operators. So we can use the operator product expansion and compute operator matrix elements to extract the splitting functions. And it turns out that if you want to compute such operator matrix elements, if you put all the scales to 0 and you're in a master situation, you get a 0, right? Because your scale is integrals, so that's not going to be useful. You have different options to introduce a scale here. And what we find is the most efficient way from the computational point of view is to introduce an off-shellness for the external lag here. And in this way, we stay at relatively simple expressions. The price we have to pay is now you go off-shell with an external lag and you're not gauge invariant anymore. So this introduces a whole lot of new problems because you now have in the renormalization, you have also, in the case of the singlet contributions, you have also admixtures of new operators which you didn't start with and which you don't know beforehand. And so two solutions to this problem have been proposed. One was presented by Giulio by using generalized BRST to explicitly construct these for a fixed moment n. And we developed in parallel a different approach, which doesn't aim at reconstructing or at constructing the explicit operators. Instead, we just compute the counter terms which we need to cancel the UV divergences of interest. And we find that this has certain advantages in our setup because it's relatively easy to go to all n results, which is the main goal of our calculation. And if you go to very large n, then these contributions become sizable. And well, this is one solution which works for us. So this is the generalized renormalization. You see you have admixtures from these gauge variant operators. And we don't care in our setup what they really are. We just look at what their effect is on higher multi-lag amplitudes with additional off-shell partons. So basically, the things you insert here as subtopologies. So we just extract what we need to cancel the divergences there, and then we plug that into the lower lag, higher loop result. And in this way, we can extract we can construct all of our counter terms. Now, in order to go to all n results, we, instead of writing down powers, which depend on the symbol n, we introduce this tracing parameter t, which resums the contributions from arbitrary n. So instead of this, we write down this expression, and at the end of the calculation, we expand again in t and then extract the coefficient of interest to get a specific power of n. And in this way, we perform a re-derivation of the three-loop splitting functions, which of course are known since a long time by Sven and company. We computed this for the first time in a general arc psi gauge, and surprise, psi cancels. So this is good. And we, of course, get full agreement with the old result. And we then went on to do a first calculation at the for loop level of previously unknown results, the NF squared contributions. And they are the integral reductions are a little bit harder and so on, but we can use all of the standard machinery now at this point. So that's good. And in this way, we end up with an all n result. And this allows us to, in particular, gain additional information in the small x region, where previous information was only partial. In particular, here you don't know the leading term for x going to 0. If you fit it from other available information, you introduce some uncertainty there. So yeah, this is what you see here is our fit, which tries to mimic to some degree the fits provided by Sven and company. So this is the fit using 20 Menon moments, and we compare that. This is the ratio with respect to the exact result. And you see that, yeah, for small x, we now have additional information in particular. All right, so let me conclude. In general, if you want to calculate some multi-loop amplitudes, you could choose numerical methods, which are easy to automate, and also avoid expression swell. However, analytical insights can help you to find better numerical evaluations, and it can also be crucial to have analytic insights if you want to do anything symbolic, because straightforward symbolic algebra is often very resource intense. Now, I showed you a couple of techniques which help you to overcome these obstacles. And going forward, I think we still have the need for better IBP reductions and improved schemes for the integral evaluation, which are, yeah, very fast, allow you to go to high precision, and are easy to automate. And something I didn't really talk about, but what I wanted to put on this outlook slide is that it would also be useful going forward if we do more of these mixed QCD electroweak corrections, or just genuine weak corrections, that we get better automation for the treatment of gamma 5. And you see here, this is a survey which we did for the SNOMAS process. So, we asked people to tell us about their computational needs for some challenging calculation they did. And you see that we start to get in the domain of where clusters are really needed. So computational improvements tend to be very useful if you want to do the next step and do something which was previously inaccessible. So thank you for your attention.
Time for questions, of course. Yes.
So you showed a lot of computer algebra programs that sort of under the hood. When you do these computations, can you briefly mention which ones are publicly available to the community?
Mm-hmm. So yeah, I skipped actually a couple. I showed a list of integration by part reduction codes which are publicly available. So this list is continuously growing. So this is a list, an incomplete list of publicly available reduction codes: fire, reduce, light red Kira, finite flow, neat IBP. This is in the order of appearance, not in the order of like, it's not a judgment how good they are, but yeah, some of them are quite powerful, and a lot of experience by the authors went into the creation of these codes. So these are rather sophisticated nowadays. But it doesn't mean that you can't do something better yourself. I mean, if you have a problem-specific solution and or a good idea, sometimes this is what you may need, because maybe these are all not good enough for what you want to do. Then, yeah, I didn't mention public codes for the generation, for instance, of D-log integrants, the construction of epsilon factorized differential equations. I listed a couple, but this is an incomplete list. This was just what we used, but there are many codes for that as well. So I didn't really aim at giving a complete overview over the field. So I apologize for that. This was heavily biased towards what we did. Yeah, there are many codes for that. And then, of course, also integral evaluation with Fiesta, Pisectec, numerical programs like that. But also what is very powerful in terms of automation and high precision are these expansion methods. So we have a whole set of new programs which expand the differential equations along some univariate slice of the parameters, and then you essentially you solve exactly some log and power tower, and yeah, this can allow you to transport information through your parameter space or your kinematic invariance, with very high precision. So this is, I think, really a game changer for what concerns numerical methods, because now we're talking about potentially 100 digits or so you can do. And, yeah.
Well, it's just a curiosity from a non-expert. So when you get to such complicated interface, such complicated diagrams, so for simple diagrams, there is a degeneracy as to where you are the routing of loop momenta, which normally, for a two-loop diagram, you can sort of see what happens. Does this play a role? Is it a difficulty? Is it a symmetry defect? I mean, does it make a lot of difference how you route the loop momenta in the calculation? Do you have to make smart choices?
I think you don't have to make a smart choice, but you have to make a unique choice. I think that's essential. But yeah, this is in principle available in these automated programs already to perform the mapping down to a unique routing. And so you can find these these relations in an automated way. If you do a problem-specific solution, then maybe you want to be smarter than that. But it's to some degree a solved problem, I would say, and it's fairly easy to generate these shifts which you need. And I would strongly recommend to actually do that before you do anything else, because you will see a lot of cancellations already at that stage, and you get that almost for free. Yeah. So, but at the end of the day, I think what you call a certain loop momentum K or so, I mean, that specific thing doesn't matter anymore at the end, but you should realize if you have relations between different parameterizations.
Okay, maybe I can quickly ask about the last point on your conclusion slide, that one should work on gamma 5. And what do you have in mind with automated treatment? Is there already some development going on, or maybe are you working?
So yeah, many people have of course looked into that, and I would consider most solutions partial solutions, because either they are not applicable directly to multi-leg amplitudes or to higher loop levels. Or it's not known. Laurent scheme, for instance. I mean, Laurent didn't specifically say something about multi-leg amplitudes, right? So
none of them had this in mind, I guess.
But of course, if you go one step back, if you say this is essentially the Toth-Feldman scheme, then you can ask what are the counter terms you would need in the Toth-Feldman scheme, which actually I like, because it seems, as far as we know, to be a consistent scheme, right? So, but you have to fix ward identities which you violate. So you need a prescription how to restore these ward identities by introducing counter terms. And people usually say these are finite counter terms, but of course, if you plug this into a higher loop amplitude, then these show up as divergences already at two loops and so on. So you want to have this under control. And from my point of view, it would be nice to have this under control once and for all, in the sense of, if you use, I don't know, for one loop calculations in, say, the Electroweak standard model, or in the MSSM, something like that, you would probably use the Feinart's model file, right, where all the counter terms are implemented already, and this way you avoid making mistakes. So it would be good to have a full list of counter terms up to the loop level you want, once and for all. So from many people are working on this, but maybe it's fair to point out Dominic Schleckinger, who is trying to go for this once and for all approach in the Toth-Feldman scheme. So I think this is I mean, I think his work is very interesting to me, at least.
Very good.
But I mean, there are other schemes using non-cyclic traces and less naive anti-commuting gamma 5 scheme and so on. But it's the scope of all of that is currently not totally known, and it would be good to have different things to compare against each other.
Very good, thank you. Okay.
Thank you. Yeah, sorry, a non-technical question, more to your nice plot on the right for this snow mass survey. I mean, were there any conclusions for this? I think there were a lot of discussions about, I mean, you are no longer in the US, so in a sense, you're out of this discussion now a little bit, but my impression was that there were a lot of discussions about whether the current computing infrastructure is sufficient to continue, you know, higher order calculations and so on in the US. So can you make a neutral statement or something?
Yeah. So maybe one of the motivations for this survey was to find out if the current infrastructure is good or not. And going forward, I mean, SNOMAS is supposed to be a projection for the next at least 10 years or so. So what kind of infrastructure are we likely going to need? And so far, lattice QCD, for instance, is known to have high computational demand, right? And they established awareness of that. They they got funding for postdoctoral positions, in particular to maintain codes and things like that in national laboratories. For perturbative computations, at least in the multi-loop domain, there's not much awareness of that this is going to be needed, at least for some of these calculations in the future. And in practice, it can be extremely important if you have, like, just a couple of machines with sufficient main memory, for instance, right? And this is not the given at an arbitrary place, and sometimes it can be important to make progress. And the other thing, for instance, would be that also, so you want to use clusters, but maybe sometimes you also have slightly different demands for the type of cluster or the type of batch policies you need to perform these calculations, because sometimes it's very difficult to predict computation times. Maybe you need to run your job for longer than the 4 hours you're granted, and so on, right? And yeah, so there are many details where I think it would be useful for the next 10 years or so, to raise some awareness of that there is need for computers more than just what sits on your desktop, and have this have the funding agencies being aware of that.
Okay, yes, sure.
So those are 2022 numbers, but at RADCore, I don't know if you were not there, or yeah. So you remember maybe there was a talk by Michael Chacon, and he showed a plot for PP23 jets, which they are now able to do, and he sort of proudly showed that plot was 100 million hours of CPU. So the top of that.
To be honest, I appreciate that, because I don't think that all of the answers we got took really everything into account in a totally inclusive way. There's a tendency to show how smart you are by saying that you don't need computers, right? Or very little very little resources. So if even Chacon needs a lot of computers, probably everyone does.
Well, right? Michael always needed a lot of compute, right? But so there is also a quick side remark. If we get into the 100 million hours CPU ballpark, then we also have to seriously think about the carbon footprint of that plot, right? Because it's one plot, right? If we make many plots, yes, and we go into billions of hours of CPU, maybe we need to just go to these computer centers which are powered by solar panels.
Yeah, thank you. That's an interesting comment. Yeah, maybe just like a follow-up remark, all of this needs to be seen also in the context of the actual experiment and the associated resources as well, right? So if we can't make the best out of the LHC data because we are not able to provide the necessary theory predictions, right, then all effort is wasted to some degree, right? Or we don't make the best out of it. So this is maybe the thing we need to compare against as well.
Just a follow-up comment again on the same plot. So I guess that all the codes that have been tested are all not public. Okay, so first comment. Second comment, typically our numbers are a factor of 10 and smaller. So, I mean, you didn't ask everybody. So for that plot.
Well, we asked people in your collaboration.
Okay, good.
We didn't ask. We tried.
So we are on the local
We have matrix results in this plot as well. Yes.
Okay.
But we didn't ask for every study.
No, because I mean, I see numbers which are typically probably we are on the lower side of the band, so that
Yes, it
because-
depends. Yeah.
okay,
Like
okay, good. So that
no, but I can point out the request we sent out regarding matrix. No?
Okay, one last comment.
You showed all these impressive results at 2, 3, 4 loop level in QCD. I don't know if you can make a comment about going to loop purely later week, if there are qualitative differences that you might expect compare and problems as well.
Yeah. Well, of course, you know the answer. It's harder, significantly harder. Yeah. And maybe if you introduce a lot of internal masses, right? I mean, your analytic life becomes much harder as well. So if you want to do something there, I mean, it's not, it's not that there's no vision for that. And I think if you have that under control, then analytic solutions can be really powerful, right? But maybe at some point becomes tedious, and maybe you have so many internal masses, such a rich structure that you might decide to use a numerical scheme. So yeah, I think that's not, what should be open-minded with respect to the possibilities and combine suitable, techniques. And maybe you want to solve a differential equation like semi-numerically using expansion methods, right? But even for that, you need the IBP reductions in some way, right? So there will be a symbolic computation involved as well. Yeah. But yeah, it will be significantly harder if you have internal masses, for sure. So yeah.
Okay, so yeah, thank you very much, Andreas.